Hello and welcome to this little presentation about LPG and LNG tankers. My name is Mikkel and my partner is Ask. In the presentation we will talk about some of the challenges about these vessels, and we will talk about the basic use of the gas products, dangers concerning these vessels, the difference between LPG and LNG tankers, the ship's stability when we're carrying these liquid gases, and we will show how simple LNG tanker is set up with cooling units.
They have vast tanks, but getting inside them is very tricky. The ships have to be in dry dock, and the tanks have to be completely purged of any trace of their hazardous cargo. This is the inside of one of the tanks, and as far as we know, nobody's ever actually filmed inside one of these before. That seems a shame, because look at it. All you need is one light, one camera. You can make a sci-fi movie and listen to it. That echo is real, analog, not a digital effect. Real sounds bouncing around this cavernous tank. There's room for 34 million litres of liquid gas in here. The equivalent volume of water would allow the average British home to flush the toilet for 1,200 years. And there are 4 of these, each at minus 160 degrees inside. Just another world. It's just crazy.
This is for liquefied gas. Liquefied gas comes from the refined petroleum. This gives you propane and butane, and is what we tank our LPG tankers with. Natural gas is what we transport in our LNG tankers, and is what we find natural in the earth or in the ground. The gases are used for household heating. I mean, we have heating here. We use it in our lighters. And it's also our propane tanks, where we also could either use it for cooking or some production of electrical power.
The interesting part of the liquefied gas tankers are the dangers concerning this process. If the pressure or the temperature are not withheld, it can have catastrophic consequences. If the liquid vaporizes, the gas is extremely flammable. Therefore, there are very high safety measurements regarding transporting liquefied gases.
There is a constant safety membrane of an inert gas. Typically nitrogen is used. Flames need oxygen to burn. If you replace oxygen with nitrogen, then you have a safety measure that is fireproof. This is called an inert gas, and this is always activated on the ship, as the opposite of a fire safety in an engine room, where the gas is stored in canisters ready to activate when the fire is registered. The sheer capacity of this large tanker, especially the LNG tanker, are just so massive that it is the energy equivalent of this liquefied gas is the equivalent of 55 atomic bombs going off at once if all this energy was released at the same time. All natural occurring resources have 3 stages of, they have a solid state, a liquid state, and a gas state. These gases that we talk about transporting in the LPG tankers and the LNG tankers are all natural occurring in gas form. They're extremely flammable in this gas form. That's why we would like to bring it down to the liquid form. The way this is done is either with a LPG tanker, where the tanks are pressurized so much that the gas liquefies. The other way we can do this is by cooling down the gas so much so that it liquefies.
LPG, as shown in the upper picture, is used when the liquid gases is pressurized to increase the vapor point, and therefore maintaining the gas in liquid form. LPG, as shown in the upper picture, is used when liquid gas is pressurized to increase the vapor point, and therefore maintaining the gas in liquid form. The tanks are cylindrical, formed and pressurized. LNG, as shown in the lower picture. This method of transporting gases is by cooling down the gas to the liquid point and keeping the atmospherical pressure. Methane and ethane has a vapor point of -161 degrees and -88 degrees. Therefore, the temperature is held at a steady -162 degrees. The tanks are spherical formed to reduce the surface area of the tanks. These extreme temperatures are expensive to maintain. Therefore, it's crucial to minimize the energy loss from the surrounding temperatures. This does, however, give some stability issues.
In this picture, a one-stage cooling diagram is shown. When the liquefied gas rises in temperature, it becomes a gas. This is not what we want to maintain safety on board the LNG tanker. Therefore, the gas is cooled by a simple cooling system. The tank's gas gets sucked in by a compressor, where the pressure is increased. This gas is then cooled by seawater. The energy is hereby transported to the seawater, and the gas condensates. It then travels through a receiver and an expansion valve to decrease the pressure once again, and hereby has transported its energy to the seawater and resets in liquid form. Here we have 3 bottles, all indicating different storage levels of our tanks on a ship. As we mentioned earlier, the stability of an LNG tanker is a big issue. And here on the first tank we have a almost maximum free surface area. On the middle one it's almost half full. It's red, indicating bad. And the green, the last one over here, is at almost maximum capacity and the lowest free surface area. So imagine if we are at high seas, they would the tanks would be lying down. We'll start with the almost maximum free capacity, where the sea would rock the gas back and forth. It would have almost no influence to the ship's stability. Over here at maximum capacity, the same thing would almost occur, because the slushing effect would not influence the ship's stability, because there was almost no free surface area. However, on the red one in the middle, it has a huge difference, because the slushing effect goes back and forth a lot and really influences the ship's stability. On normal tanker ships, this is hindered by making baffles in the tanks, but especially on an LNG tanker, where the temperature has to be so low that that the gas liquefies. If you would create baffles inside of the tank, it would also create friction, and thereby increasing the power demand for the cooling system.